Hello everyone! This was your assignment from last Friday, and I wanted to go over a few of these problems to make sure you know how to do them. So let's take a look at the first one. We're doing red-green color blindness problems, which is an X-linked recessive trait, meaning that this gene is found on the X chromosome. And remember that in order for females to have this, then they're going to have to get it from both their mother and their father and have two copies of that recessive allele. In order for males to have it, they're going to only need one gene, one allele from only one of their parents. And because they get their X chromosome from their mother, it's going to come from mom. All right, let's look at this first problem. A woman of normal vision marries a man who is colorblind. What type of vision may be expected in their offspring? It says the woman is heterozygous for this trait. All right, I'm going to have to write a little bit bigger here. So this is her genotype here. And we're going to use how about a big R for normal vision and a small r for red-green color blindness. It says she has normal vision, so I know that she has to have at least one big R. But then it says that she's homozygous for the trait. So that tells me it's actually two big R's. All right, there's her genotype. So I can go ahead and put that onto the Punnett square. And then it says the man is colorblind. Remember, he's XY. So he's colorblind. He's going to get a little r. Remember, nothing goes on the Y. Looks like this box is going to be big R, little r. Hard to write small in these little boxes. This is big R, little r. Remember, always write the dominant gene first, recessive second. So those were the daughter boxes. So it looks like both boxes have normal vision for daughters, but they're both carriers. And then XY boxes here bring down the big R. Nothing on the Y. Bring down the big R. Nothing on the Y. All right, looks like the two boxes that show the genotypes for the sons, for those possibilities, looks like they both would have big R and therefore would have normal vision. So I wouldn't expect anybody, any offspring in this family to have red-green color blindness, but I will expect maybe to see it in future generations if these daughters are carriers or heterozygous for it. Let's do number 3. So for number 3, a woman of normal vision whose father was colorblind. So let's work that one out. So she has normal vision. We know she has to have at least one big R. But it says her father was colorblind. That means that her father's genotype looks like this. So he could have only given her an X with the little recessive R for red-green color blindness. So that tells me that she is a carrier. Marries a man who has normal vision. So he's got the big R. Go, now we can fill in the boxes. Got big R, big R. That daughter is homozygous for normal vision. This daughter is heterozygous or a carrier. So they have a daughter, 50% chance that it's homozygous, 50% chance carrier. Then for the son boxes, the XY filled in there, I'll expect that it's a 50% chance if they have a son that it will be normal vision, but a 50% chance red-green color blindness. All right, so that's a couple of the red-green color blindness problems. So let's take a look at the hemophilia problem, which was the last one on that worksheet. Hemophilia, again, is a disorder, a mutated gene where you can't create proteins to clot your blood properly. So big H is normal. Little h is going to be the recessive mutated allele for hemophilia. And this is an X-linked trait, so it's on the X chromosome. A woman who is a carrier for hemophilia, so that tells me she is big H, little h, marries a man who's normal for blood clotting, who gets a big H. What are the chances their children will have hemophilia? So let's put her genotype onto her H's. She's big H, little h, because she's a carrier. He is big H. So then in each box, we've got big H, big H. This pen is not very easy here to make drawing, so I'm going to expect 1 out of every 2 or 50% of their daughters to be a carrier. We have big H here, big H, little h there. And then for the sons, 1 out of every 2 or 50%, if they have a son, will be normal blood clotting, and 1 out of 2 or 50% if they have a son will have hemophilia. So this is the same Punnett square for the last Tsar from Russia with Nicholas and Alexandra, and then their son Alexis, who had hemophilia. All right, so that's a little rundown how you do those problems. In case you are having trouble, let me know if you have any questions.